So this part of the Advanced Lab Experimental Techniques lectures will focus on the use of detectors in spectroscopy. And we'll look at a variety of the common optical detectors, focusing on photoresistors, photodiodes, and then charge coupled devices, and also photomultiplier tubes. So just to recap, in a generic spectroscopy experiment, we have some sort of radiation source. We have to have some kind of optics to source optics. You then have the sample you're actually looking at, some signal processing optics, and then we finish with the detector, where of course what we're interested in is things like its sensitivity and its sampling rate, and some of the capabilities. So basically got a choice of two potential mechanisms for measuring a light sensitivity. So we can either go for photoconductivity, where essentially we're trying to measure a photocurrent, or you can look for a photovoltage. So on the photocurrent side, we're looking at principally things like photodiodes. So the essential operating principle of these is that they have a semiconductor with a direct band gap. So when light falls onto that semiconductor, it can create electron-hole pairs. And then you arrange for those electron-hole pairs to move apart through the application of some voltage across the device. And so what you're doing is you're actually creating charge carriers in the semiconductor. And we know from things like the Drude model that the conductivity is then going to go as the sum of the number of electron-like hole carriers plus the mobility, and the number of hole-like charge carriers and their mobility. So what we see is that in a low light level, this device can have a very high resistance, which unfortunately is then quite difficult to measure. In the bright light, the device also becomes insensitive because you end up creating so many charge carriers that you can't really create any more charge carriers, and so you don't notice the any more intensity in the light. But there's this mid-range where you get a nice logarithmic dependence on the number of the number of charge carriers you created, and therefore on the resistance. And of course you can always choose how much light your detector can see by putting an appropriate filter in front of it. So the fact that it tends to saturate or it tends to suffer in a low light level is not necessarily a problem. But of course what it is going to do is it's going to mean that you have a limited range over which you can detect the light, so that if you have a signal which goes from very, very dark to very, very bright, then that's going to be difficult. Of course, you're also reliant on it having a band gap that is suitable for detecting the wavelength of light that you're interested in looking at. So again, that can limit the operating range, and you have to choose the right sort of material. And again, with any kind of semiconducting material, you have to be careful that you don't have impurities in there, because they'll create states that sit inside the energy gap that can then act as places where the charge you've created can either recombine quickly, or else where you don't necessarily create an excitation that you were expecting to. The other side of it is more in the photovoltaics, and most of these then work with a p-n junction. So again, the principle is basically the same. Incoming light creates electrons and holes in the semiconductor, but now because you have a p-n junction, what happens there is that the electron and the holes naturally tend to separate out. And so again, you can see this as a change if you measure the current voltage characteristic of the detector. So typically what you might see is either a change in the current at zero bias, a photocurrent, or you see a change in the voltage at zero current, so a photovoltage. And both of them can become ways of actually detecting the change in the light level. And again, there the question is about choosing the right semiconductors with the right band structure in order to go and measure them. If you want to go to the next level of a slightly more sophisticated detector, then one of the common ones that gets used is a charge coupled device. So at its heart, it's just behaving like a like a photodiode. So you have a p-n junction and you create the charge carriers through the emission, the absorption of the light. So just to show how this works, so we start off with our detector in its quiescent state, and in comes the photon, and that's absorbed at the P and N type interface, creating an electron and a hole, which then move apart. So that's our standard photodiode response. But then what we do with the charge coupled device, we go to the next step on, and we put another junction in there. So we have an N type, a P type, and an N type. So it's actually a transistor. So when you have two PN junctions stuck together, you get a transistor. So a charge coupled device is using a phototransistor. So what happens in this case is, again, we have the device in there. So, and in its off state, what we find is that you have a collection of electrons, because it's an N-type semiconductor, and because we're changing the doping of the N-type semiconductor as well. That's the other important thing in this device. So what happens is you have a collection of electrons sitting in the N layer at one end of our circuit, and they can't get to the N layer at the other side of the circuit because of the P-type barrier. So what happens in this case is, again, we turn it on, the electron is absorbed, and an electron and a hole pair are created. And then what happens is, as the hole moves into the P-type, that then changes the potential of that P layer relative to the two N layers, because what's happening is you're changing the occupation probability of the valence band there, because we've introduced extra holes. And so that shifts the Fermi energy relative to the bands. And then as a result of that, the potential barrier that was created is dropped. And all of a sudden you get this rush of N charge carriers through into the base of the device. So you get this amplification effect, because although we only created one electron and one hole, what you've ended up with is a whole burst of current coming through. So that's one individual phototransistor. But what gets more useful is then when you can go and build a whole array of these things next to each other. And that then is the proper charge coupled device. So what you have is a P and an N layer. And then on top of that, you have a gate dielectric. And then on top of that, you have an array of gates. So again, what happens here is you have the photodiode effect. The light is absorbed, and electrons and holes are created. And then what ends up happening is the electrons fall into the N-type layer, and the hole goes into the P-type layer. So the hole is then lost from the system. But now you've got an electron sitting in the N-type region. But also what you've gone and done is you've applied a gate voltage with those series of gates. So by applying that gate voltage, we've dropped the potential of the N regions. We're actually reverse biasing our diode here. But it's only being reverse diode laterally. So on the top direction, it's only been reverse biased under those individual gates. So the electron is then held under those gates, so it can't go anywhere. So now in order to go and read it out, what you do is you apply, you drop the voltage on the gates sequentially in turn, and then shuffle the electrons along. So if I drop the potential that's on the gate that's one over from the rightmost electron there, then I can allow that electron to flow into the next bucket over. And then we repeat, we move that gate potential onto the gate, the third gate along from the left, and then that'll drop the barrier to let the second electron move over, and then we do it for the second leftmost to the gate, and we drop the potential and the leftmost electron moves over, and then we repeat the process, and we're able to sequentially move those electrons along from pixel to pixel to pixel until eventually we can collect them all at the end. And so what you do is you do this sort of shift register type operation where those electrons are moving along. Why is this a great way of doing things? Well, because it's a multi-pixel detector. So now you're able to go and detect not just that you received some light, but exactly where you received the light as well. And if you build your structure right, you can also then encode pixels which will respond to different wavelengths of light. So you're able to get color information as well. And so a charge coupled device is basically what's going on inside your phone on your camera, on the camera on your phone. It's the kind of imaging detector that's used on every single mobile phone. And of course, that means that you can therefore tell we've got technology which involves very, very, very large pixel counts. You get a very good spatial resolution. And that's very useful because it means that if you put the correct dispersing optics, like a diffraction grating or a prism, you can then go and spread out the radiation according to its wavelength and detect exactly what wavelength you had by virtue of where it landed on your detector. And as a result of that, you can rapidly sort of in parallel measure lots of different wavelengths simultaneously, and thereby extract a lot of information in a quick single burst measurement. Okay, so then the final type of detector I'm going to talk about is the photomultiplier tube. And these are particularly valuable when you've got a single photon event that you're trying to detect. So in this sort of scenario, what happens is that your single photon enters a scintillating medium. So this is something where it'll undergo some photoabsorption and then cause some photoemission events. So this might be, say, for example, a very high energy photon. So say like a gamma ray coming in from outer space, hits the scintillation chamber and creates one or more photons. And then that photon that you've created travels to the photocathode layer. And the photocathode is a material that's designed to release electrons when it's hit by light. So light comes in to the photocathode, and that causes the photocathode to emit an electron. To get the amplification effect, we then use a whole series of electrodes, each one of which is biased at an increasingly high voltage relative to the previous one. And although it's not shown in this diagram, you also have to do some shielding to make sure that as your electron produced by the photocathode moves through the system, it only sees one of those dinodes at a time. So what happens is the photo electron is emitted from the photocathode, travels towards the first dynode, and it's got a sufficiently high voltage that when it strikes, it's got enough kinetic energy that it's able to dislodge another electron. So you get some secondary electron emission. So that way you get, say, 2 electrons traveling out from the dynode, and they go to the next one, and that then gives you 4, and then 8, and then 16, and then 32. And you can see that after not very many stages, you've suddenly geometrically multiplied your original signal. So rather than having just 1 electron hole, which is what you would get per photon, which is what you were getting in the semiconductor detectors, you're now getting many, many, many electrons per photon. And so this is genuinely a single photon resolving detector. The disadvantage with it is that it tends not to be sensitive to the frequency of the incident light, because as long as you go over the threshold to cause a scintillator to scintillate, then after that you're going to get a big pulse of current. And of course there's also then a certain amount of reset time as well. But within those limits, they make very good single photon detectors. Of course, if you want to go and do any kind of imaging or to resolve where exactly that incoming photon came, then there's no real way around it other than just having a shed load of these photomultiplier tubes all on your detector. So this is where you get into the realm of the big science. So for example, this is taken in a solar neutrino observatory. So solar neutrino observatories have to be built deep underground because you're trying to make sure you don't get any so-called dark counts, because if you have some kind of spontaneous generation of a photon inside this detector, then what's going to happen is it's going to set off your photomultiplier tubes, and then you have to wait for your detector to go and reset. So there is some dead time after a photo detection event. So by burying the observatory deep underground, you're trying to shield out as much of the way you can in terms of high energy cosmic ray events. And you're relying on the fact that the neutrino, by definition, does not interact with very much at all. And so you're hoping that although you don't have much neutrinos interacting with your detector itself, there are sufficiently few other events that you're able to go and pick up the detection events that are only caused by the neutrino. And so in this case, you've ended up with over 9,000 photomultiplier tubes in the one instrument. And of course, then you can imagine just how much power and how much back processing electronics is needed. So these sorts of detectors are seriously big science. Finally, another kind of class of doing detection, and this is particularly useful when you're wanting to know about a wavelength dependence, is to use an interferometer. So the basic concept of an interferometer is that you make use of two paths, or the radiation going through two paths and then interfering with itself. So kind of the simplest example of this is, of course, a Young's double slit. So in this case, the incident radiation goes through two slits. And then after that, the radiation travels through essentially the same part of the experiment. So it's a common path. And so you then obviously pick up the characteristic diffraction pattern. Slightly more sophisticated for use actually as a spectrometry instrument is to use something like a Mark-Sender interferometer, or there are various other designs as well, the Michelson-Morley interferometer or the Fabre-Perot interferometers. And what's going on here is we're splitting our radiation beam into two paths by using a series of partially reflective mirrors, or beam splitters. So at its simplest case, a beam splitter is just an angled plate of glass, because what happens is you have some of the light undergoing a reflection and some of the light undergoing transmission. And you get that split between reflection and transmission because the light is seeing an abrupt change in the refractive index, or an abrupt change in the impedance. And as we know, if you have a medium with an abrupt change of impedance, then what that tells you is that you have to have a change in the amplitude, because some part of it is reflected and some part is being transmitted at that change in impedance. So that's what goes on in the beam splitter. And in this case, you angle the beam splitter so that the reflected beam goes one way and the transmitted beam goes the other way. And you can then take those two paths of light and you send one of them through the thing you're trying to measure, the sample, and then afterwards recombine it with the beam that hasn't gone through the sample, and then you can look at the intensity of those two mixed beams. And because you started off, assuming your light source is phase coherent, then what you'll find is that any change in the optical path length due to the sample will be detected as a change in constructive or destructive interference by the time you get to the detector. And what you'll also see is that if you say, even if you don't change the phase going through the sample, a change in intensity is also going to change the amount of the amplitude of the interfered pattern. And the reason you have two detectors in this case is because you want to ensure that you're collecting all the light that's going through the instrument, because you want to make sure you're sensitive to both the any fluctuations in your source light level as well as what your sample is doing. So what you end up then with is looking at the two detectors at components from both bits of both optical paths plus the interference going through both of those parts. And by looking at the sum and the difference of the signal from those two detectors, you can work out how much of the changes you're seeing is due to the overall brightness of your source changing and how much is due to something happening in your sample. And interferometers is a much more general concept, so you don't have to restrict yourself to light. Anything which can behave like a wave can be used in an interferometer. And so an example down here is where we're using a matter wave in our interferometer. So in other words, we're looking at a system where we have a macroscopic quantum mechanical wave function. And the classic example of where you get a macroscopic quantum mechanical wave function is in a superconductor. So inside the superconductor, there are electrons that are forming pairs. Those pairs of electrons then have an integer spin. So although the individual electrons aren't bosons, the pairs of them behave a bit like bosons. It's not quite as simple as saying they are bosons. But in particular, they're boson-like in the sense that they can be described as inhabiting a single quantum mechanical state. So because they inhabit a single quantum mechanical state, that means I can write a wave function for them, which just has a single wave, a single phase that extends over the entirety of the superconductor. So that superconductor can be microns, it can be kilometers, but the electrons in that superconductor you could describe with this single quantum mechanical wave function that covers all the electrons, no matter how big the superconductor is. And that means you can start playing interference effects with the superconducting electrons. So this particular device is called a superconducting quantum interference device, or SQUID, and it consists of a ring of superconductor which is interrupted by two weak links where the superconducting electrons can couple across it, but in a limited fashion. And then what happens is that if there is any magnetic field coming through that loop, that field causes a current to flow, so it induces a current to flow around in the loop. And then because you have a current flowing around in the loop, on top of what the electrons were trying to do anyway, then you get a phase difference in the quantum mechanical wave function from one side of that loop to the other side of that loop. And due to that phase difference, you get interference effects in measuring the current flowing all the way through the structure. And in fact, when you do the maths on this, and this is part of the fourth year superconductivity module, it turns out that the maths exactly resembles what's going on in Young's slits. So we're doing the same type of interference experiment with light in the case of Young's slits, and with the wave function of electrons in the case of the SQUID. And because you now have an interferometer which is sensitive to the magnetic, well, strictly it's the magnetic flux coming through that loop, then you have a magnetic flux sensor, which turns out to be incredibly sensitive. So you can measure very, very, very small changes in magnetic flux. And you're essentially acting like an interferometer. And that not only does it mean you have a very, very sensitive magnetic field sensor, so it can detect things like the magnetic field changes due to the neurons in your brain firing. It's that kind of level of sensitivity. You can also use it in other ways. For example, you make a very sensitive current sensor, because if you place a little coil above it and then have a current flowing through that coil, then that produces a magnetic field in the coil, which then couples into the SQUID, and then you detect that magnetic field with your SQUID. So it becomes this incredibly powerful sensor, which is all just using the same basic concepts of interferometry that we got from the Young slits experiment.